Hello everyone. So I'm going to talk about methods like data assimilation to try to obtain better estimation from coupled atmosphere fire modeling. And along the way, actually, it's like we have worked on several components because if you want to have a good data assimilation algorithm, you need to have good data, good observation, and you need also to have a good model, good prior information. So I will talk about all these elements, provide an overview on what we are working on, because we have lots of projects starting this year, as Cyril mentioned, with the urban program. And as Bati mentioned, I work in collaboration with Météo France, CNRM, and in particular with Patrick Lemoine, who is an expert in land surface modeling, and we have currently a PhD student, Margot Perrault, working on fuel modeling. And Ronan Pogam is here also because I worked for a long time with Ronan on how he has infrared data, how to post-process them, and we work together on how to integrate them in data assimilation system. Okay, so my outline for today will be I work at geographical scale, and for now we are at small scale, like small fires, a few tons of hectares. I will talk about some work we are doing on the coupled atmosphere fire modeling, in particular on some components, on the validation, on the uncertainties we have and how to quantify them. And then through data assimilation on how to reduce them. But building a data assimilation for such a system is quite challenging, as there are different methodological issues, and especially since we are dealing with a front problem with wind direction that has significant uncertainties and makes some topological errors in the model. Okay, so what I want to emphasize here, is that just a motivation to work on that is that with, for instance, the extreme fires in Australia a few years ago, we have seen that individual fires can have regional to global impacts. And so we really are on this question on which processes drive the development of large-scale fire, and to understand the interaction between the fuel effects and the weather-dominated effects on the rate of spread, and how you go from a surface fire to some extreme phenomena such like ground fire spotting and pure convection. And actually, the system we are trying to build is really to understand the interaction between the fuel and the weather effects. So why are we working with the coupled atmosphere fire model? Through some preliminary sensitivity analysis, we have seen that wind is a predominant factor, and we really want to capture how the wind is modified by the fire and this fire-induced wind, and see its temporal variability, how it can change over time across an event. Because, for instance, if we look at the rim fire in California in 2013, you see that you have some days where one color is 1 day of propagation. You have some days with very large areas that are burned, and you really want to know, to detect when these days can occur. Okay. So the coupled fire atmosphere model we are working on is in terms of the fire spread model component, we are using Blaze that was developed by Aurélien Coste during his PhD. And it's like S-Fire in the water fire. It's a level set method, so it's an Eulerian framework, and we have a parameterization of rate of spread. So for now, we have a BALB formulation that was developed here at the University of Corsica. And the Blaze fire model, actually, it runs on a grid that is a refinement of one cell of the atmospheric model. So we are using here meso-NH, like Bati. And then when you couple this fire spread model to the meso-NH atmospheric model that runs in LES mode, and for now runs at decametric resolution, so like a 10 or 25 meter resolution, the variables that are exchanged between the two model components are, so we are extracting the near surface wind from the first height of the atmospheric model, so like 2 meter or 4 meter height. And we provide this wind velocity to the fire spread model, and this is an input to the rate of spread model. And then the fire spread model has a simplified surface heat flux parametrization. So we know the arrival time of the fire front, and then we have some parametrization on how the heat flux evolve over time once the fire arrives at a given point. For sure, this could be refined using observation, and if we, yeah. And one aspect of this is the special, the temporal variability of the heat flux. But there is one important aspect when we are in the context of a coupled fire atmosphere model is the vertical profile of the heat flux. You cannot inject the heat flux only as a surface heat flux, because the atmospheric model is too, it's a too strong signal for the atmospheric model, so we need to have some smoothing over the vertical, and this is something that is for now set up in an arbitrary way, I would say, and so observation could also be useful to calibrate this heat flux parameterization parameter. Okay, as a starting point, we have worked with in the frame of Aurélien Cos's PhD, we have worked with the fire flux experimental grass fire, and we were able to do some simulation of the fire front propagation and of the plume with passive tracers. We don't do chemistry yet, and it's not planned so far. We have already lots of things to work on the dynamic part. And one thing, let me see. And one thing we were interested in with this case is to look at uncertainties. So you have different types of uncertainties. You have what we call the model representativeness. So there is a question on how far should we go, how detailed should we go into the physics representation in the coupled model. Here we have worked on, in particular, on the canopy wind-fire interaction. And then another, I will talk later on. And another source of uncertainty is the inputs of the coupled model. Either we don't know them very well, or there are some spatial temporal variability. So what I call inputs is the near surface wind that is seen by the rate of spread model, but also the state and type of the live and dead biomass fuel. And so the question is, how can we quantify and reduce these uncertainties? Just some examples to illustrate what we have been doing. So it's the same simulation as before on the fire flux cases, but what we have seen is that for validation, it's very hard to validate such a simulation against the observation if you have only one deterministic simulation. So actually, what we have done with Aurélien is that instead of running one simulation, we have an ensemble of simulation, and each simulation starts at the fire ignition in each simulation starts at a different time. This is to have some different realization of turbulence and of the boundary condition, and actually it has a strong influence on how the fire will propagate over time and over the grass burn plot. So the fire is ignited here in red. Don't look at the green, just focus on the red and blue simulation, so that it's two different resolutions. And then, for instance, for the red at 10-meter resolution, for the atmospheric model, you have the ensemble mean fire front, and you have the envelope, so the spread within the ensemble. So that you see that actually the envelope of the 10-meter resolution ensemble has the same spread that the difference between the 10-meter resolution and the 25-meter resolution. And what I want to point out here is that it's difficult when you look at your model and try to calibrate it and to find the best configuration. It's difficult to separate the effects of should I go to this 10-meter resolution? What is the initial condition? You can have some effects that have the same impact on the fire front position, and so this is an issue we have. But with this experiment, we have seen that it's really important to have at least to have an ensemble to do a comparison with the observation, not only having one simulation, but an ensemble one. To have an ensemble one. To have a stochastic approach. Another aspect I would like to show is another PhD student that just defended this year, William Antolin, and with him we also worked on this fire flux simulation, and actually this is in red. This is the burn plot that was only covered by grass, but around it you have some forest cover, canopy covers, like especially on the northern part. And actually the wind is in this direction. So this canopy block is small, but it's just upstream of the grass plot. So the question was, does this canopy block have a strong influence on the propagation that will occur from the ignition point through the grass burn plot? For this, we were able to run again a simulation, coupled atmosphere fire simulation at 10 meter resolution with an ensemble as Aurélien, but we had two sets of simulation, and one set was only, we assumed there was only grass, so no canopy, and the other set of simulation activated the tree drag force. So in Methane H, you can either represent a forest as a roughness length, this is the classical way, but you could also activate some terms that in the turbulent kinetic energy equation and in the momentum equation, you can activate this tree drag force to really explicitly account for the interaction between the trees and the wind. So we were able to run this simulation and to show that this forest canopy block has an impact on the near surface wind that is occurring over this plot before the fire and during the fire. To show that, we have done an analysis of quadrants. So you look at the fluctuation of the wind velocity component. So here you have the surface, the surface wind component, and here fluctuation, and here the vertical wind component, the fluctuation of the vertical wind. And so you have this data, for instance, like over 1 hour before the fire, during 1 hour, and you can put the values on these quadrants. And you know that when you have a forest canopy, classically, you have this asymmetry in the quadrants. So we have sweeps and ejections that are typically typical events that occur, typical turbulence events that occur in canopies. And within fire flux experiment, we have seen that if you look at this fluctuation over at the main tower, over the burn plot, so it's grass, you can see that we recover this asymmetric quadrant. And so in the observation and with our simulation with canopy, we are also able to have this asymmetric quadrant, while in our case of only grass, you don't see it. So this type of analysis is very interesting to see that when you go to very high resolution, like 10 meter resolution for a field scale experiment, you have an influence of the forest canopy on the wind that is occurring over the grass burn plot. So this is before the fire. And during the fire, you have also the effect of the heat flux released by the fire, so it's more difficult to see. But what we have been able to show is that if you look at the fire front propagation and you look at the arrival time of the front at this main tower, okay, and you have an ensemble, so you are able to do some statistics. So what is the spread of the arrival time here? You see that it's not the same if you look only at the grass only simulation or if you look at the canopy simulation. And this arrival time variability is plotted with respect to the distance from this canopy block. So as you go further away from the canopy block, so as the fire propagates, you see that the variability of the fire front arrival time is growing. And so this shows the importance of having an ensemble. But also what you see is that close to the canopy block, there is quite a huge difference between the grass simulation and the canopy simulation. And we think this is due to the trail of the canopy. And this shows that all the canopy block upstream influence the fire front propagation and influence the turbulent structures that are occurring over the grass burn plot. And this is really important to know at which speed the fire will propagate. Okay, so this is one part more on the model, and And we have also now another component we are working on since last year with the start of the PhD of Margot Perrault, and also with a project that just started, that is just starting, is to work on the inputs of the couple model, and in particular on the biomass fuel modeling. So we would like to represent, so this is a map of the vegetation types as seen by Meso-NH or by Surface in the models of Météo France. So this is at 300-meter resolution, and we have like 19 different types of vegetation. And our idea here is to define a fuel model for each of this type of vegetation. And we focus so far on the Mediterranean area because it's where we have also observational data from the Réseau Hydrique network, led by INRAE and Office National des Forêts. And our goal with the PhD of Margot is to see what is the added value of including all the live description, the live component of the fuel, and in particular including the live fuel moisture content information, and see how it changed the rate of spread evaluated by the root-ML model. And within EcoFeu project, the idea is to go a bit further. These fuel models are static, so we want to have some dynamics, some temporal variability, because you have some seasonality in the properties of the fuel parameters. And so the idea is to include the information of tree dieback to update every year the fuel models, the fuel properties, and then to have also some seasonality if you have some droughts during the season, you know that the tree will lift out earlier and things like that. So we work on that with CNES and CESBio to integrate information from satellite remote sensing to improve our fuel models. I've said that already, so we'll move forward. And really the idea behind working on these fuel models is, at the end, in our couple model, for now, we only represent the surface fuel and the surface rate of spread. But if you want to work on large-scale fire events, we need to work on also what is the possibility to go from a surface fire to a crown fire and things like that. So this is really a preliminary work before going to model crown fires. First step. For sure, when we are dealing with such a couple model, the validation is a really important part. So we are really happy to be within the urban program, and in particular this urban risk project that is just starting. And we hope that with the field campaign, we will have lots of data on different fire cases that will be useful for validation and comparison with the couple model simulation. And in terms of the model, our objective is to go, so far I've shown idealized simulation for field campaigns, idealized fire propagation, but we want to go towards a more realistic workflow. And for sure there is a question on how to initialize the model with satellite data and for fire, as you have seen before. There is a question of representing the biomass fuel model heterogeneity over this part of Europe. And also for like fire flux, we were at 10, 25, 50 meter resolution. And the question is, can we degrade the resolution, and to have something running faster? Why? Because we want to have ensemble of simulation and things like that. So we would like to study the dependence of the representativeness of the model given with respect to the resolution. So, okay. So all this is our work to have to better understand what do we need as components in the atmospheric fire models, and the validation is an important part. But actually, when we go towards data assimilation, how to say, you want really to integrate all the information in a given workflow. So the idea of data assimilation is to combine all the source of information you have on the fire behavior. So you have this coupled model, but we also want to benefit from the infrared observation. And there is a question of how to combine these two sources of information on the fire behavior. And so there is a question on which observation we assimilate, how to have a representative ensemble of the different scenarios of your fire behavior. And you want to compare both to obtain a feedback to solve an inverse problem and retrieve information on your inputs of your model and correct some uncertainties you have on your fire front propagation. So what we have seen on a simplified framework before, while we were not using a coupled model but only a fire spread model, is that for observation, it's interesting to go from infrared observation to fire front. So you need to do some work on segmentation of infrared images, as Ronan talked about yesterday. Here, if you have a coupled model, then it's hard to have your coupled model within this workflow because it's computationally intensive. So what about building an emulator of this coupled model, and within the data assimilation workflow, you use the emulator instead of the physical model to obtain robust statistics. And then for the inverse problem, actually for such a problem, lots of uncertainties come from the input, from the near surface wind forcing, from the fuel properties that we don't know very well. So what you want to do is not only state estimation like in weather forecast, but you want to estimate both the fire front position and some influential parameters, input parameters of the model. Ronan showed this case yesterday, the Savannah fire, where you have a time series of infrared images. And actually, we have done some work using deep learning based on convolutional neural networks to extract fronts from the infrared images. And so it was not only one CNN, it was more like a series of CNN to really annotate all the images from the data set. And so, And in the end, the idea is to obtain a burning map where you have the arrival time at very high resolution. So here for this case, it's like in the Savannah fire in Kruger Park, it's like you have a 1 meter, 1 second resolution of your arrival time map. And this is really valuable data to test the data assimilation system, to see what is the frequency at which you should assimilate the data and things like that. So lots of work on this part, but deep learning is really helpful for this. Another issue when you want to assimilate fire fronts is that it's not a standard data assimilation problem. It's not like you estimate the temperature, which is an amplitude error. When you have a front, you have position errors. And actually, some people from NCAR, for hurricane tracking, and also from University of Colorado and for wildfire, they have shown that standard data assimilation may fail if you have too substantial error differences between the observation and your model prediction. Because the standard method, what they try to do is to, instead, actually, what they tend to do is to generate artificial structures when they want to, instead of changing the position of the front to have a simulation that is more consistent with observation, what they do is that they create artificial structures. And so for a hurricane, instead of having one, you have two. It's an issue, and for fire, it could do the same. So the group of Jan Mandel have developed some new methodology to overcome this issue. And we have also worked with INRIA, so it's an applied mathematics research institute here in France, to find a way to better compare simulated and observed front. So I don't want to give details here, there are some publications, but the idea is you want to have a measure of the similarity of the front, and actually your cost function to do that has two components. You both maximize the hits between your two burning area, and you want to minimize the misses, what you miss from the observation. And this measure was derived from the image segmentation field from the Chan-Vézé functional. So it's quite technical, and we are still working on it, but it has shown some promising, some potential. And if I show you, we have done a proof of concept on a field scale experiment like the Eric Scudder experiment in the US, where you have a mix of shrub and grass fuel, and if you have here the aerial time map, so the fire starts from here and propagates over 15 minutes in this direction. And we have applied our joint state parameter estimation problem with this similarity measure to see if it works. So it was part of the PhD study of Kansang in collaboration with the University of Maryland. And what we were able to do is, if you have the observed front, you see that with your data-driven algorithm, we were able to track the observed fire fronts over time. And we do not only track the front, we also, over time, correct the wind speed and the wind direction that is used as an input to the rate of spread model. So you see some variability of the wind parameters that is retrieved over time. We cannot validate that this estimation is realistic because we didn't have this type of data, but it's something that we will do in the future on an application where we have this type of measurements. Okay, and now, so this work was done. Quite a while ago, and in between we have worked a lot on the couple model, and now there is a new project starting, Firefly, where we want to see how to extend, how to design, how to adapt this method to a couple model framework, to the Meson H-Blaze model. And I will have a postdoc starting in January to work on this. And yeah, in the different things we want to study is that first we need to define which fuel parameters we want to estimate, which one has the most influential of the fire front. So for sure the dead fuel moisture parameter is an important one, but we could do something like a global sensitivity analysis to see on a given case what are the 2-3 parameters that are really important to estimate. There is this work on the front differences that we want to continue with in RIA, because for now we have done it in a deterministic approach, but we need to work on how to include uncertainties within this cost function I mentioned. Once you have a couple model, it's very costly, so there is a question of testing emulation strategies to integrate an emulator instead of the couple model within the data assimilation workflow. With another PhD student, Elliot Limay, we have developed a method combining principal component analysis with Gaussian process regression that is very efficient to emulate LES data at a micro scale. But in this case, it was without having a hot source like a fire. So we will see if we can adapt this method to our fire configuration. And for now, we will test this approach on field campaign data. So we think we'll start with the savanna fires I showed and Ronan showed yesterday, because we have lots of data, front data at high resolution, and we want to test our algorithm, what is the frequency at which we should assimilate the data and things like that. So we think we will start with this case. So just a plan, we'll see how it goes in the next years. I think I am now at the conclusion. So now, yeah, lots of work and lots of different topics, but the idea at the end is to build a reference model for simulating fires at geographical scales, and this is really done in a joint collaboration between CERFAX, where I worked, and CNRM. As Baptiste said, we are on the same campus in Toulouse, in France, and for now we have two main aspects we investigate. So how to improve the fuel modeling, and how to do a very robust model evaluation, accounting for uncertainties, and also we want to go to cases of increasing complexity, and we hope the eBurn program will be helpful for that. And so once you have the reference model, you know that you still have uncertainties, and so the ultimate goal is to build a reanalysis capability, is to see if with our model and combined with the data assimilation approach, we can reconstruct the detailed chronology of a fire event And so if we have this, then we hope, we could really investigate what are the driving physical processes that led to the fire front propagation, and then at some point to why do we have large fire for some situation. But to go there, yes, there are some methodological aspects we have to investigate. So how to do a proper front data assimilation and which fuel parameters are important to estimate. So I thank you for your attention, and if you have questions, I will be happy to answer.